definitely could, you know. So is it likely? Well, it's less likely, you know. But all right, so let me go on here. So I wanted to do a proof, another truth table proof that we haven't done yet, just to give you one more example of a truth. I'm having trouble saying truth table proof for some reason, but let's work on the following proposition, which is that P, if and only if Q, and Q, if and only if R, all right, is that implies that P, if and only if R. I think I might be able to get away with well, I wanted to put I wanted to make this a double arrow here, but I think that's actually not true. So let's see here. That feels wrong to me, though. Oh no, okay. Well, anyway, this is fine. I'm sorry. You know, the funny thing is we use the word proposition. This is like, we use this word in the same way we use like the word theorem, you know? So I think that may technically be a slightly different use of the word than the definition we introduced last time, which was what is a proposition? Do you guys remember what we said? Connection error. What? Come on, you stupid thing. You know, this used to have buttons that let's try unplugging other cables here. All right, anyway. So here we're dealing with the question I asked you guys hadn't answered me yet. What was a proposition? Last time we said a proposition is a declarative sentence that has, you know, a value. It's either true or false, right? So it has a definite truth value. And I was trying to give you an example of something that's not a proposition, and my mind just blanked. And well, I come up with that stupid example of all dogs are beautiful, right? Which was not helpful. But there's a much easier example. What's a sentence which is not a proposition? There are many of these in the English language. Yeah.
Questions?
Yeah, any question is a great example. You know, is the dog beautiful? That is definitely not a proposition. Okay. Okay, so here's the truth table proof. We have propositions P, Q, and R, right? Now, if we've got 3 propositional variables, we're going to have to do what? I may regret this. Let's see here. We have 8 cases, right? So I'm going to kind of use the analog of the ordering I did last time, right? Which is false, false, false. False, false, true. So basically I'm going to have 4 falses and then 4 trues in the first column. The second column is going to go false, false, true, true, false, false, true, true. And the last, the R column is going to go false, true, false, true, false, true, false, true. All right. If you do this pattern, it gets you all cases, right? There are 8 cases for 3 propositional variables. This is my reward for top hatting today. See that? That's what happens. So let us look at the biconditional P if and only if Q for this column. All right, and we'll look at the biconditional Q if and only if R for this column. And then we'll look at P if and only if Q and Q if and only if R in this column. And then I see I have to extend my lines just a wee bit more because then this last column will be the claim of the proposition, which is P if and only if Q and Q if and only if R implies, sorry, it's kind of, for those of you with the OCD, this is probably going to bother you a bit, what I just did, but you guys can deal. So any questions before I go on? What am I doing right now? I'm trying to prove this claim of propositional logic. The method of proof I'm using at the moment is just basically case-wise analysis, but it is our custom to use truth tables for such a thing because nobody wants to read 8 paragraphs, right? I don't. Do you? However, it is common in mathematical proof writing, if you only have like 2 or 3 cases, you might not use a table. You might instead use paragraphs or something, you know? Okay, anyway, so you guys tell me, this first column here, P if and only if Q, what do we got? True. True. False. False. Yeah, false. False. True, true. All right. And Q if and only if R, what do we got? True. Oh, false. Yeah. False. True. True. False. False. These are kind of relaxing, aren't they? Now to get the next column, we're deciding the conjunction of the statement, you know, P if and only if Q and Q if and only if R. So to get this column, I need to look at these two, right? If those have the same truth values, then that's true. If they don't, if they're both true, this is true, right? Otherwise, if there's even one of either of these columns which is false, that next column we're doing is false, right? So I can just look through here and find the truths. That's when I'm doing an and, what I do is I look, okay, so this is true. Is there any other one that's true? Just that one, right? So those are the only 2 cases which are true for this and operation. Everything else, there's at least one or both are false. So these are all F. Hopefully, you know, not a grade in this class. Let's see here. So, I'm sorry, too soon? Let's see here. I mean, anyway, if you stay to the end of the class, I almost invariably will award a D if you do everything, you know. I only give Fs pretty much to people who just don't come to class and stop doing stuff. So, all right, anyway, so that's a little consolation, because if you get a D, you have to take the course again, right? But at least I'm not, like, you know, killing your GPA as much. Actually, I'm not doing anything. It's all on you. I take responsibility neither for your success nor for your failure. This is your business. I will try to help you, but that's all I can do. Okay, so this one, P, so this is the implication, right? So you guys tell me, what's the deal here? How do we think about this? The only way, so for an implication, it's kind of opposite of and, right? There's only one case that makes it false, right? Which is true implies false. So I pretty much just look for true implies false and I write F there. Everything else has to be T. That's the easiest way to do this. So I'm looking for true implies false, looking at, oh man, you know what, I failed. Oh, come on. Dudes. Sadness. Sorry. So this was the final one. I forgot that we don't have that column yet, right? My bad. Sorry about that, guys. I like to put some brackets on this kind of thing because otherwise I kind of get, I mean, technically speaking, the brackets aren't needed, but I think it helps. All right. Okay, so P implies R then. That conditional, what's the deal? The only way that can be false is if we have true implies false. Do we have any of those? This one. And this one. Oh. We used to have drawstrings. A string wrapped around a spring. All you did was pull it down. We never asked for this. It automatically comes down, means it can't automatically go back up, which you can see this could be a problem. Anyway, so there, do you guys agree with me? All right, so now we can judge this implication. So we're looking for, I'm going to look for the false case, which would be true implies false. Is there any true implies false here? There's not. So what's that make this? Yeah, it makes this a tautology. In other words, so that was, I think I failed to finish the proposition, is a tautology. My bad. Sorry, guys. It's not too late, though. There we go. So, and then like the conclusion is here, thus, you know, the proposition is true by the truth table. Sometimes if you look at my work, you'll see that I stop short in the truth table of the last thing, and I write the last thing in the sentence which I conclude with. So I might make a step in my concluding sentence to avoid writing one more column in the truth table. That's a move that I sometimes make, right? But one way or the other, there has to be a complete conclusion to the thought for the proof to be complete, right? And this proof is still not quite right because it's missing the preamble, which is what? How does this proof have to start? I almost always will write a little, like this is just my custom. I write proof colon like this just to announce to the reader I'm starting the proof, all right? And then I need a sentence up here, right? I say this. I say let P, Q, R be propositions, period. And then I say consider, comma. Now the proof is complete, all right? You're like, you're going to take points off if you don't write that? Yeah, probably. Not a lot, but enough so that you notice. And like the goal of you know, this class is for you to learn to give complete logical arguments, all right? Although, thankfully for all of us, the word complete, I don't mean it in the technical sense, right? Like, I'm not going to make you build the real numbers from scratch or anything like that in here, right? So we do work in a certain formal way. Let me show you something else here. So this is the proof, the proof table. Proof table, listen to me. Truth table proof. And like everything on this sheet I'm handing you guys can be proved in this fashion. All right, so here is a handout. I got 4 handouts for today. Here's the first one. There's going to be too many, so you guys will have to pass them over because I can't count. So pass them over and up. So I wanted to also show you another guy's, listen to me, not a good sign, another proof. So this is, here's a formal column style proof. So here, so I'll start with my proof. Let P and Q be propositions. All right. Consider let's see here. Make sure I got the right one. I wrote out a couple things last night, and I'll make sure I'm not showing you guys the wrong one. One was more interesting than the other. Yep. There's 2 extra papers. Are they all passed out? You have an extra? I can pass it over, yeah? Are there more in the back? That one's coming for you. Got it? Oh, I don't know. Anybody else? Okay, cool. All right, so, all right. The claim that I'm going to make here is that P implies Q is logically equivalent to not Q implies not P. All right, this is, now we already know this. We proved it by a truth table last time, right? What is that? What's that called? The contrapositive. Right, the contrapositive is one of our favorite tautologies. So I want to show you kind of a quick example of a column style proof. Now, oh, well, my bad. Poor planning on my part. I should have done something before I started this proof, but you know what? I'll fix it by adding a lemma. What's a lemma? A lemma, let's see here, which one do I actually need? Give me a second here, guys. Yeah, the and. P and Q. Actually, instead of using P and Q, let me use, I need something else. My apologies for using capital T for a propositional variable in your homework. Sorry about that. So, let's say R and S. If and only if S and R for S R propositions. So this lemma I'm stating is somehow missing on this list of properties of the logical operations, right? Like this is missing for our list, but it's kind of basic, right? I would call this the fact that the logical and is commuting. I would think of this as commuting is the label I would give it, right? P and Q is the same as Q and P. And the same is true for logical OR, right? If you were to say S or R is the same as R or S. Now this I'm going to prove with a truth table. So here's the proof. So consider propositions R and S. We've got R, we've got S. We've got false, 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 true, true, false, true, true. So I will write down R and S here, and S and R there. So of course I've got what? False, 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 true, false, 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 true, So then R and S, if and only if S and R is, of course, a tautology, right? So the lemma follows. Now, as a point of personal style, I write like a line in class when I'm like done with a thought, a proof. This just completes the proof of the lemma, though, all right? Now let me return to the proof of the claim in the top. All right. I'm sorry, I need to, I'm trying to show you good writing, and I get ahead of myself sometimes. So we really don't want this here at this point. Like, we just want to start the proof with, consider the following lemma. All right, done. Now that I'm about to do the proof for this guy, I'll say over here, like, continuing, consider propositions P and Q. All right. So first of all, we'll begin with P implies Q. This is logically equivalent to P, oops, my bad. My P became an R. P and not Q. And then over here I write by theorem 1.1.14. All right. Now look at the paper I just handed you guys out. Do you see where that is? If you look at your paper, one of our two major theorems collecting, proposition, theorem, propositional calculus, if you will. That's one of our tautologies, right? So I can do that. And then next, so this is a standard format of mathematical writing. We write a stack of things like this, where we give the reasoning over here, but this is basically just one long run-on sentence, all right? So P implies Q is logically equivalent to P and not Q by theorem 1.1.14, which is logically equivalent to, next step, not Q and P by the lemma, right? With what? I mean, I can just say by the lemma. If you don't understand what I'm doing, I'm specifically letting R equal to P, and I'm letting S equal to not Q there. Do you guys see that? Okay, so I'm using the fact that logical and commutes there, which we proved in the lemma. And that is logically equivalent to not Q and not P. Not P, which is by, oh man, I'm sorry, I neglected a number here, guys. That was by 8. We can do better, right? By number 8 of theorem 1.1.14 in the previous step. Yeah. And this is by 1 of theorem 1.1.14. I wish I had I regret having the name of this theorem 1.1.14, which is kind of annoying, but it is what it is. So, yeah. Then, what can I do? This is logically equivalent to what? So can you guys see what the next step would be? Q and P. let's see here. So what is this? Let me just, okay, so this is scratch work, all right? Let me put the scratch work in a different color. The bridge between implication and logical and is this number 8 on theorem 1.1.14. What does that say? I'm going to write it. So it was, what was it? P implies Q. It is logically equivalent to what? Not P or Q. Wait a minute. Yeah, not P or Q.
So wait, wouldn't that be then not Q and P?
Oh, hold on. Oh man, my eyes jumped when I was writing this thing out yesterday. Oh, rats. Yeah, this is not true, right? See, we actually have to do what it says, you know? Because, well, I mean, all right, so this is or, right? This is or, okay? Oh man, this is annoying because now my lemma is not helpful to us, right? So, all right, let me make the corrections here in red. All right. So this was supposed to be an or. That's actually number. That's what 8 says, right? All right.
It's not P. It's not P, Q.
Oh. So not P or Q?
Yeah.
All right. Which is what I have up there. Okay. And then by the lemma 2, lemma 2. For R and S propositions, we have R or S if and only if S or R. Right. Proof. Left to reader. This is a move only I'm allowed. Okay. You can try that on your test as well, but if you do that, then the reader gets the points. So, reader being me. Let's see here. But you guys know how to, I mean, the proof of lemma 2 is obvious, right? Same thing we just did, but replacing this and with or. Yeah. Okay. So then we've got this not P. Let me make the corrections in red over here. So that, instead of this step, we would do Q or not P. I think that's what we want to do by lemma 2. And then I'm going to convert my Q to not Q. I did prepare for this class. I spent like 30 minutes writing this silly thing out. You wouldn't know it. All right, so this is not Q or not P by 1 of theorem 1.1.14. All right. Then what I want to do, so this is I'll put my scratch work up at the top here. Like, think of this as S implies R if and only if, let's see here, not S or R, right? And so if we look at this, we can think of this as what? Like S equals to what? See the idea? The idea is I can use S equal to not Q, and I can use R equal to not P, right? I can make that identification, and then I can write that this is logically equivalent to S implies R, which in this case would be not Q implies not P, and that's by 8 of theorem. I really should have given this thing a name. 1.1, which is less annoying than that. Therefore, thus, the claim holds. And this completes the proof, all right? Now, is this the right proof to give for this? Obviously not, right? What would be a way easier way to prove the contrapositive? Truth table, right. And indeed, my truth table for the lemma was as complicated as the proof for the claim just itself, you know? So I'm not trying to show you this as an example of like the best kind of proof for this claim. The purpose of this example is to illustrate a format for you, which is the formal, you know, column commented formal proof, all right? So that's the purpose of this example. I have another one to give to you in a handout. So let me do that. And this handout also has a definition which we will read together, but I won't. You don't need to write it out really. We're going to live this definition out, all right, in this class, pretty much. So one of the main customs of mathematical proof writing is proof is read top down, right? Like you start with the start and you end with the end. And the general rule is that whatever you've done in the proof up to the point where your reader's reading is supposed to be considered as the reader considers the next step, right? So extra. There you go. All right. You know, I'm glad I made these copies today because the thought had gone through my mind, use the projector, you know, and see where I'd be right now if I had relied on that projector. We'd be waiting another 30 minutes for it to not work. Okay, anyway, so definition 1.21, and these numbers are from my notes, right? So statement Q is said to be a propositional consequence of the statements P1 through Pn if and only if the single statement P1 and P2 and Pn implies Q as a tautology. We often drop the term propositional and simply refer to the consequence for the sake of brevity. The assertion Q is the consequence of some list of statements that's called an argument. The statements in the list are called the premises or hypotheses or givens of the argument, and Q is called the conclusion of the argument. If Q really is a consequence of the list of statements, then the argument is said to be valid. All right? I believe what I just gave you here was an argument to establish that claim. Right? It's a list of propositions, the net implication of which is this truth, right? So, and then here I have proposition 1.2.3 from the notes, all right? And here we have the claim that, oh, this is actually the one we were using, right? That P implies Q. Oh, notice the very important, what's the difference between this proposition 1.2.3 versus what I had written on the board and erased? There's one small but important difference. The parentheses around P and not Q. No, that's not it. It's the not. Yes, that not is everything. And that not is what was not in what I wrote to start with. So there you go. This is proposition 1.2.3. All right. And here is a formal, this is a slightly different style of formal proof. This is actually even more formal. So this is, my bad. This is actually not a, this is a, sorry, I've forgotten my legalism here. Technically speaking, believe it or not, this is an informal. This is an informal. The reason it's informal is that the formal column style proof is even more litigious, right? Like notice what's the difference between my informal column style proof that we have up there and the one on the paper you're looking at here, the formal. It starts out the same proof, right? I say formal. That doesn't have to be there. That's just for the sake of drawing your attention to that word in the notes so you know what I'm talking about when I refer to it later, yeah? Let P, Q be propositions. So far we start the same. But then I've got the number 1, right? Number 1, P implies Q if and only if not P or Q by 7 of proposition, theorem 1.1.14. So I won't go through all these, but the point is that they're numbered, right? And the other thing that's kind of obnoxious about this formal proof here, like look at step 3, right? Look at step 1, we have the logical equivalence of P implies Q and not P or Q, right? Number 2, we have the logical equivalence of not P or Q and the not of, not P or Q, right? What's step 3? Step 3 is to combine steps 1 and 2, right? How can I do that? So I'm using 6 of theorem 1.14. What is 6? Sorry, I got to find my paper. Uh-oh. Do you guys see a problem with that? Well, anyway, let me not belabor the technicalities here. The larger point is just this: is a formal column style proof. You like number each thing like that. I think this proof may be flawed actually, because I was originally laboring under the delusion, guys, that this. So going back to the start of class, I had this idea, and apparently it's false, right? That if I have P if and only if Q, and if I have Q if and only if R, that gives us P if and only if R. I really want that to be true, but I don't think it's true, because if you look at this column here, right, and that column here, if we haven't made a mistake, can you move that camera? If we haven't made a mistake, I can't make this a double arrow, right? Because why? See this? They have different truth, false values. So, but it is true. The implication is true, right? But I think when I wrote this formal column style proof here, I think this presumes that that's an if and only if I understand things correctly. But sometimes I talk myself out of correct arguments that I've made and make them incorrect in class. So let me just hedge my bets and say, let's go on, rather than trying to fix what might not even be a mistake in this formal proof. Okay, so that's it. That's pretty much all I've got to say to you guys about propositional logic. So we move on, and now we will talk about the predicate calculus. So I have yet another handout for you. So what is the difference between a predicate and a proposition? We already sort of spilled the beans last class. What was the difference between a predicate and a proposition? A predicate is based on a function. Yeah, predicate has some variables, right? Some kind of mathematical variable or some sort of, there's something ambiguous about a predicate which makes the predicate either true or false depending on those ambiguities, right? So we also call a predicate an open statement. So a predicate depends on, one or more unknowns. Everybody got one? Right. Uh-oh. Where's my extra? There's got to be an extra in here somewhere. All right. Sorry. So let's read together here for a bit. A mathematical variable is some symbol or combination of symbols that represents some unspecified number or other object. The collection of numbers or objects from a particular variable can take its values, that it can take its values in is known as the domain or the universe of the variable. All right. Variables with the same domain are known as variables of the same sort. Like a lot of times in calculus and pre-calculus, we talk about real variables, right? So the domain of a real variable is the real number system, right? Before, in like middle school algebra, you might have looked at variables which were integer valued variables, right? So like if you can't factor using integers, using whole numbers or their negatives, you'd say it couldn't be factored, right? Like this is something you might uncover. You might run into this in like an intermediate algebra class, for example. So for different kinds of mathematical variables have different kinds of domain, all right? So that's one thing. A notion which transcends different categories of variables, though, is the idea of a constant variable, right? So a symbol or a combination of symbols that represents a fixed number or other object is called a constant symbol or simply a constant. All right. Now the next definition is important. We need to write that one on the board. So, I mean, every definition is important here, but the ones I write on the board are the ones that I'm more likely to put on a quiz. So. Also, I don't know, some of the, like, you can kind of get a sense of, some of these definitions are really, well, I think most of the definitions in logic are really just setting terms, there's not, it's a little bit different than the kind of definitions we tend to run into in mathematics later. I mean, we're really just trying to resolve arguments people are going to have about what implication means. Or something, right? Because like the question you guys raised last class about isn't false implies true, isn't that not legitimate? So we just define it to be true, right? That's implication. Okay, so this is the definition. The symbol upside down A is read for all, is the universal quantifier. It denotes the phrase for all or for any. There's various different language or for every, and which one of those you use kind of depends on, well, it's a matter of style, right? What sounds best to the ear, if you will. The symbol there exists, which is a backwards capital E, is the existential quantifier. It denotes the phrase there exists, all right, or there is, all right, or for some. All right. So let's see here. So definition 1.38, the next one here. A mathematical variable occurring in a symbolic statement is called free if it's unquantified, and it's bound if it's quantified. If a statement has no free variables, it's closed. Otherwise, it's called a predicate, an open sentence, an open statement, or a propositional function. All of the x for which the proposition open statement p of x is true is called the truth set. So let me give you an example of that. All right. Let's see here. So actually, let me stick with my examples in the notes because it'll keep us out of trouble. So this is example 1.3.4. I think we can decide along the way here whether or not the variables are bound or free. All right. So I think it's going to be kind of boring for this first example, but it'll get us started. So here's the deal. We'll let q of x denote the open sentence x is a rational number. We'll let r of x be x is a real number. We'll let z of x be x is an integer. All right, so those are some open sentences we're defining for the variable x. All right. So given that, we can translate some sentences, right, into symbolically quantified statements. So like here's the first one. Each rational number is also a real number. Let me switch colors here. Each rational number, can't spell. Each rational number is also a real number. So this you can trade for the symbolic statement for all x. All right. For all x, r of x. My bad. Rational is q, isn't it? Let's see here. For all x, q of x implies r of x. So this symbolically says each x, which is rational, is also real. Another sentence we can symbolically quantify here, if I can find a marker I like. I'll jump to the next one here. Some real numbers. Some real numbers are also natural numbers. Well, let me switch that out for integers since I failed to write n of x. So I'm changing my notes a little bit, that's fine. Some real numbers are also integers. All right, so symbolically, we can write this as there exists x such that what?
R of x implies z of x?
Nope. Not like that.
x implies r of x?
No, it's not an implication. Here, what you want is r of x and z of x. Because what this sentence means is that there are some numbers, which are both real numbers and integers. Not all, but there exist. Now, so a for all statement and a there exists statement, they're logically different animals, right? So I have some more examples. The next example in my notes, I've got a silly example. X is a cat is the statement C of x. X is a... Actually, let me skip ahead and do the example after that. I'll leave you guys another example to read. Oh, so I read the statement about bound and free variables. What do you guys think? If you look at this example we just did, is x, in these statements, is x bound or free?
Bound.
Is bound, that's right. So, as a general point of order, if we have an open sentence and we slap a quantifier on it, either there exists or for all, it may be the case that it's no longer an open sentence, it's now a proposition, right? These statements here, right, they have definite truth value. They actually happen to both be true, right? We can write a proposition which is false. They don't have to be true, right? Like, can you guys tell me if we just flip this around, right? Like this is a false proposition. For all x, r of x implies q of x, right? That would be false, right? Why is this false? Since we have what? We've got like square root of 2 is in the real numbers. However, square root of 2 is not in the rational numbers. So this statement is false because in order for this statement to be true, it must be the case that for all x, that implication holds, right? If there's even one where it fails, right, it is true that x equals to it's true that x equals the square root of 2 is a real number, right? So the antecedent is true, but x being a rational number is false. So that makes the implication true implies false, which makes the implication a false statement, right? But nevertheless, the thing I wrote in green is a proposition. So by taking an open sentence and quantifying it, we may obtain a proposition, all right? Although, if there is more than one variable involved, we might still have an open sentence, right? In that case, you'd have like a free variable. Let me go see here. So like my next example is kind of silly. It's not really a mathematical example. Example 1.3.6. We have m of xy is one sentence, f of xy is another sentence. So m of xy is the statement x has mother y. F of xy is the statement x has father y. All right? So here's a sentence we can try to make a symbolic logic statement of. All right. Everyone has a father and mother. I think that's still true at the moment. Right? The transhumanists haven't had their way yet. We're not copying people's on a machine or anything, right? So, I don't know. I watched this interview with Tucker Carlson about this one of the guys, one of the 4 people who invented the Chat GPT apparently, who was like apparently murdered, but like it's being covered up. It's fascinating stuff. If you haven't seen that interview, I highly recommend it. Okay, so everyone has a father and mother. We can write this symbolically. There's different ways. So one way we could write it would be, for all x, square bracket, there exists y, parentheses here, m of xy, and, I gotta close my parentheses matter here, and there exists z such that z f of xz here, close square bracket. So that's one way you could write it. For all x, there exists a mother for x, and there exists a father for x. Right? That is another way of saying the sentence, everyone has a mother and a father. Right? Notice that the symbolic sentence, clarifies the, well, I guess it doesn't clarify, but, distinguishes the role of father and mother, So, another way you could write this would be the following. You could say, for all x, there exists y, there exists z, bracket, m of xy, and f of xy. The thing I wrote in blue above might be the right way to look at it if you were trying to do something like negate the statement. If you were trying to negate a statement, it might be helpful to have it written in the format that I have in blue. In some sense, what I wrote in black is really a shorthand for what I wrote in blue. All right. But there's an even shorter shorthand. So for all x, there exists y and z, m of xy. So I think these are basically in order of increasing brevity. All right. So if there exists y and z, we can write like that. Example 1.37 I will not write on the board, but I will read because it's fun. Any questions? So how about this? X and y in this example. Is one free? Is one bound? What's the situation here? Are we looking at free variables, bound variables? What's your feeling? Is there any free? Let me ask the question in a more leading way. Is there any free variable in this example? No, not down here anyway. Only up here. Up here, these x has mother y. This sentence has 2 free variables, x and y. Right? Both of these have 2 free variables. But once you quantify them with these quantifiers down here, they're bound by the quantifiers. All right. So this is the language. Now, so my next example is very silly. I say, suppose x is a human living in Virginia. Let b of xy denote the sentence, x is the boss of y. All right. And let j of x denote the sentence, x is a two-faced annoying loser. Sorry, I lost the quote here. And then, I'll write down the symbolic part of it. For all x, there exists a y, parentheses, j of x, and b of xy. All right. Versus, so the point of this example, besides just being silly,